In this video, we'll talk about another method for proving that Taylor series converge to the function that we want them to. It's more complicated, but again, because it's more complicated, it gives us better results in terms of this convergence and other examples we can use it for. So now we're going to talk about another theorem for when Taylor series converge and using that to actually do stuff. Here's our theorem. Let I be the interval from c minus r to c plus r, some interval centered at c like the power c stuff from before, where r is bigger than 0, and assume that f is infinitely differentiable on I. What that means is that anywhere on this interval, I can take as many derivatives as I want. I can take 10, 30, 100, as many derivatives as I want to take. I can take them all there. If they're 0, that's fine, but I can take them. They exist. Secondly, suppose there's some number k, bigger than 0, such that every derivative is bounded by k. Not just each derivative is bounded by a different k, but all the derivatives are bounded by the same k. That's a pretty strong condition, but it's enough to make sure that this works. If we have that, so if I have a function that's infinitely differentiable and all the derivatives are bounded by some number, then I can represent f by its Taylor series in I. Namely, if I write the Taylor series for this function f, which I can write out because there's infinitely many derivatives, then this series exists, this series converges, and it converges to my function f everywhere in the interval I. So the point is, this boundary condition here is very strong, but it's strong because it gives a big and strong result. The question then becomes, what kinds of functions can we use this on? What kind of functions do we know that have derivatives that are all bounded by some number, no matter how many derivatives I take? Well, the key examples here are sine and cosine. Why? Well, these functions are bounded by 1, and they go back and forth derivatives. They go from sine to cosine to sine to cosine, and those are also all bounded by 1. So k equals 1 here gives me this result works for sine and cosine because the derivatives are all bounded by 1 everywhere. So let's go ahead and see, can we do this for sine? Let's find the Maclaurin series for sine of x. Maclaurin meaning it's centered at 0, so I'm plugging in 0 whenever I do things. What am I going to get? So what's f at 0? Here my function f of x is sine of x. If I plug in 0, I get sine of 0, which is 0. F prime of x is going to be cosine. So f prime at 0 is going to be 1. F double prime is negative sine. So f double prime at 0 is 0. Third derivative is going to be negative cosine, which at 0 is going to be minus 1. And this pattern is going to repeat, right? Because then I'll get back to sine, which is 0, and then I'll go 0, 1, 0, minus 1, 0, 1, 0, minus 1 along the entire series. This pattern of 0, 1, 0, minus 1, and so on is what I'm going to get every time. So let's try to figure out what this looks like in terms of the actual series. So the series then, we're adding up from 0 to infinity, nth derivative at 0 divided by n factorial x to the n. The first couple terms I get here are going to be 0 over 1 x to the 0 plus 1 over 1 factorial x to the 1 plus 0 over 2 factorial x squared plus negative 1 over 3 factorial x cubed, and so on. What we notice is we're only getting the odd numbered terms. So what I can do is I can rewrite my series to only hit the odd numbered terms. So I can write something like sine of x is going to be sum from n equals 0 to infinity, and now I want to only hit the odd numbered terms. So I'm only going to look at x to the 2n plus 1, because that'll start at 1 and then count up all the odd numbers. Now what's the coefficient of x to the 2n plus 1? Well, it's going to be negative 1 to the n, because it's going to go plus 1, minus 1, plus 1, minus 1. And I'm starting at 0, so that starts with the plus 1. And what's underneath? Well, it's going to be 2n plus 1 factorial, the same factorial as the power that I have on the x. So this here gives you my Maclaurin series for sine of x. That's the easiest way to write it. Simplest way to write it out is that one right there, and that's what you want to have known for this Maclaurin series. So in terms of Maclaurin series, what do we have? Well, we know the sine of x one we just did. And again, because we know that sine of x has bounded derivatives, and this power series converges everywhere, then we get the Taylor series converges to sine of x everywhere. We can also do the cosine one as well. And it looks like that. With the cosine one, you'll get only the even terms showing up, but the idea there is exactly the same. And we also know e to the x. These are our three main examples at this point of Maclaurin series. And these are ones you'll need to know going forward to be able to use them for other examples and things in the future. That's our other result that we have about proving that Taylor series converge. It's that if I have bounded derivatives, which work for sine and cosine, it only kind of works for e to the x. Be a little more careful if you do this for e to the x, but you can still apply it there. You get that then the series converges, and it converges to the function I care about everywhere on that interval. This gives us new examples like sine and cosine that we now have Taylor series for and can use going forward.